Got the right things on there. And I didn't adjust this ahead of time. So we're talking about today, Chapter 3, Part 2, projectile motion. I wanted to start out by just touching base with where we ended last time on Monday. So let me see if I can do this. Share screen, and then slideshow. Okay. So we kind of, on Monday, gave the definitions of velocity and acceleration as vectors when we have two-dimensional motion. The generalization to three-dimensional motion is, there's not much difference there. It's just that these vectors a path wouldn't be, restricted to a plane. It might, wind through three-dimensional space. But it's based on the same definitions that we used in one dimension. In other words, acceleration is change in velocity over change in time. Velocity is change in position over change in time, except that those velocity and position things are now vectors rather than just what we would now call x components. The acceleration is just the average acceleration over a very short period of time, and I have to calculate the magnitude of an acceleration or velocity by using the Pythagorean theorem. Okay, let me just start out by, I grabbed a bunch of reading response questions that these ones sort of mostly looked backwards for the material that we did on Monday. So let's just quickly go through these. We'll talk about the newer material that we're going to go briefly through today. Then we'll do a few more reading response questions. Then we'll start into a lot of problem solving. I understand that the vector of the change in r is found by connecting two spots in time on an xy coordinate plane with the arrowhead on the second spot for time. When finding the change in velocity vector for a similar graph, do you connect the tail of v1 to the tip of v2? No, you don't. And let's go back here to just look at this picture here. Here we've got an ant crawling along a path, or maybe it's a remote control car moving on the floor, which is the xy plane. And we would say if it's here at t1, it's here at t2, then the displacement vector, of course, as was said in this reading response, just points from the t1 location to the t2 location. Now I've drawn in the velocity vector with its tail attached at t1 and the velocity vector at time t2 with its tail attached at t2. And of course, they're tangent to the curve. We talked about that a while back. And the question was about the change in velocity vector. Do we go from the tail of this one over to the tip of this one? And the answer is no, not if we have it in this configuration that's drawn on the path there. The change in velocity vector always means a difference. And if you want to draw a difference, one way to do it is to draw the tails at the same location. So here I've transported those velocity vectors so their tails line up. And then I draw between one tip and the other tip. So you can't really do it directly from this picture by going over there or something like that. You have to actually move things around. Second question, if gravity is always acting upon objects, does that mean that an object or person has to push off the ground with greater than 9.8 meters per second squared acceleration to lift off the ground? And what is keeping us from just falling to the ground instead of standing up straight? The answer here is no, you don't push with a certain acceleration. If I treat myself just as a rigid body, clearly I'm not, so there's kind of not just one position of my body, but we could imagine I'm roughly moving like a ball. I could say, right now I'm not accelerating at all, right? I'm just sitting here. Despite the fact that the acceleration due to gravity is 9.8 meters per second squared, I am not in free fall, so that doesn't really apply to me, right? Gravity is not the only force on me. The floor, fortunately, is pushing upwards and sort of counteracting gravity. And we'll try to make sense of that a lot more in Chapter 4. So that's coming up on the reading you're supposed to do today. But I can accelerate upward with much less than 9.8 meters per second squared, right? 9.8 is a pretty fast rate of acceleration. Maybe that's too light to accelerate at the right rate. But you accelerate from rest really quickly at 9.8. I might, slowly start going up like that, and I could make myself accelerate much less slowly upward than 9.8. But the important point here is that there's only one acceleration that a body has. I shouldn't think of it as my body is simultaneously accelerating downward at 9.8 because of gravity, and because of the floor, it's simultaneously accelerating upwards. No, I'm a body, and I only have one acceleration vector. Right now, it happens to be 0. I could make it change and go upward or downward, right? If the floor falls away, I'm going to start accelerating downward. If I start pushing upward against the floor, I would start accelerating upward. So there are many forces that act on me, and again, we'll talk about this more in chapter 4, but only one acceleration for any given body, at least if it's a rigid body. Third question, because we're ignoring air resistance, all objects have the same constant acceleration when they're in free fall or in ballistic motion, free fall when they're going on an arc through space. When we finally start looking at air resistance, will the acceleration still be constant? My thought is it might be constant just at a slower rate than 9.8 meters per second squared. That would be nice, but it's not true, and that's because air resistance is sort of a strange force where it hardly acts at all, hardly pushes on an object at all when it's moving slowly, but the faster it goes, the bigger the force gets. And we'll find that that affects the acceleration more and more, so that when an object starts falling, I'm not going to let my water bottle go into free fall, but if it starts falling, it is going to at first have almost 0 air resistance, and that means it's going to be very close to a 9.8 meters per second squared acceleration. But as time goes on, its acceleration will become less and less because the air resistance pushes back on it more and more as time goes on. A lot of these things will kind of come together, I hope, in chapter 4. Example 3.8 this is looking ahead to something we haven't really talked about yet, but 3.8 uses the trig identity 2 sine cosine equals the sine of 2 times the angle. Are these identities something we should review? No, you don't need to know these identities, and you don't really need to know how to get that range equation. And in fact, I am never going to pull, in the process of problem solving, pull the range equation out of a hat that you read about in the sections that you read for today. Rather, you can always answer those range kind of problems just starting with the kinematics equations, which is exactly where Giancarlo got the range equation from. But if you want to memorize that equation, it's fine with me. It is somewhat restrictive. It only applies to something that leaves the ground and comes back down to the horizontal ground, so it starts and ends at the same height. Tells you something about how far it goes, but it can't leave from this height and end up on the floor. Then the range equation wouldn't apply. But our kinematics equations would apply in that case. We'll see those examples today. Many, many good questions on there, but I tried to pull some that are representative. There are more later on in here. Okay, so as usual, just to sort of high level summarize what you saw in the videos, we're now going to imagine ignoring air resistance, that someone throws a fairly dense object, so air resistance doesn't really matter so much. In an arc through space, we're going to put some XY axes somewhere on the image. And, at least for the purposes of this example, maybe right after the ball leaves this person's hand, we'll call that t equals 0. And it seems like the x coordinate of the ball and the y coordinate of the ball should be functions of t, and our goal is to find those functions of t. It also seems like vx and vy should be functions of t, and we can actually find them pretty easily now that the work has been done back in chapter 2. Again, we talked about an object in free fall back in chapter 2. The same thing is true when it's moving in 2 dimensions, but still air resistance is negligible, that the acceleration is oriented directly downward towards the center of Earth, and the length of that vector is 9.8 meters per second squared. That's free fall acceleration. So in this coordinate system, because I've chosen plus y is up, ay is negative, and ax is 0, right? And going from tail to tip, I don't have to move along x at all. That's what ax equals 0 means. So now I've got a situation where something's moving both in x and in y as time goes on, but the x acceleration component is 0, and simultaneously the y acceleration component is 0. We would just call that a constant acceleration vector. It's the same at all these points when it's in free fall or in ballistic motion like that. So we can repeat the same argument that Giancoli gives in chapter 2. I didn't really give it in class, but it involves either integration if you're in a calculus-based course, or Giancoli probably argues in terms of areas under curves. And this, we can just sort of do it twice in a row. If AX is constant, then all three of these follow. That was just chapter 2. But if AY is also constant, these three follow. And the only difference between these equations is that all the X's have turned into Y's in the other one. And so there's not, if you have memorized these, I know there's just a lot of stuff in here, but after we've finished with this chapter, you should find that you have an easier time remembering these three equations. And there's really only three. It's just the X and the Y that have changed there, because we will have used them so much in chapter 2 and in chapter 3. So if you still have to commit them to memory, that's fine. But I think almost by osmosis, you would have gotten it from the sheer amount of problem solving we're doing. Okay, so one of the properties of these equations is that there are no y's on the left-hand side, and there are no x's on the right-hand side. And that means for this special case, where we've got a constant ax and a constant ay, that the x motion is totally independent of the y motion. In other words, this vx0 represents the initial x velocity component, the vx0 there. How fast something is moving just with respect to the x direction at time t equals 0. The fact that that symbol doesn't appear over here means that how the object falls with respect to time doesn't really care how fast you shot it in this direction. It still falls at the same rate, whether you shot it really fast in the horizontal direction initially or didn't give it any initial horizontal velocity. And sometimes that's called the independence of the horizontal and vertical motion of balls. Another way to look at this that I had in the video also, ball rolls off a table with various speeds. Here's if it's going pretty slowly, and here it's going faster, and here it's going faster. And these are supposed to represent sort of Strobe's pictures where those balls would be at a certain time. And they're all at the same height with respect to the floor at each time. The horizontal motion is changing, but the vertical motion is unaffected by that initial x velocity that it had as it left the table. And here's a little demonstration that is, at least shows that in one limited respect. I have no idea how old this thing is, but it's totally encrusted. It was somewhere in the back of our demonstration area. So there's two brass spheres, and they've got holes in them. And there is a little spring-loaded mechanism here, and I can push against the spring and push this rod out of this end. So what I'm going to do is, it has a lot of friction, so I got to kind of work it over to just go against the friction. But you'll see on the left-hand side, there's a little rod that's protruding, and then I can put this thing down to hold it there. So the spring really wants to shoot it in that direction, but these little clips are holding it. And what I'm going to do is put one of the brass spheres on there. One's a little bit tight, so let's use this one. And I'm going to put the other one over here in a little divot that's right here on this table. And I have to make sure if this is going to work at all, make sure it's completely horizontal, at least as far as I can see. Okay, so one is just sitting up there, and one of them is being supported by that little rod that's protruding out this side. And when I flip this thing up, what's going to happen is that rod's going to shoot, because the spring is trying to push it in that direction. Rod's going to very quickly shoot in that direction. That's going to leave this ball unsupported, and it's just going to fall downward. And it's simultaneously going to knock that one with an initial horizontal velocity. And the claim is we'll see this kind of motion that's being illustrated up there. Now, it all happens so fast, it's hard to see it with your eyes. So I would suggest that you rather listen with your ears to the bounces on the floor, and hopefully we'll hear both of the balls bouncing at the same time as they come to rest on the floor, if everything is lined up the right way. Ready? So it sounded like one ball. That was actually two balls bouncing, and each of the bounces were at the same time. So That's just demonstrating that giving a ball an initial x velocity has no effect on how fast it falls in the y direction. Okay. So I also made the point in here that we're making the assumption when AY is minus 9.8 if plus Y is up, and AX is 0 if X is horizontal, that if those are only true if gravity is the only significant force acting on the object that is falling or flying through the air. If I'm throwing a ball through the air, so I toss it up, in the time when I'm holding it in my hand and pushing it, that's not true. Gravity is not the only force on it. My hand is a significant force. And when this ball falls to the ground and hits the floor, as soon as it hits the floor exerts a really large force on it too. So we can't include the time when my hand or the table is still touching it. We can't include the time when it's hit the floor. And so you'll often see in these kinds of problems, I use this slightly awkward phrasing. The initial state I'll use is just after leaving my hand, and the final state just before hitting the floor. Because if you say the final state is when it hits the floor, it's like, well, did it stop then? Or it's sort of confusing, but just before, we all know it's still moving only under the influence of gravity. Okay, so we're about to do some problem solving. There were some examples in the videos, and I'm not going to go through them in any detail at all, but the same kinds of things we said that you ought to keep in mind in chapter 2 apply here too. You have to choose which way your axes point, the plus direction for x and y, and where the origin is. So we got to do both x and y axes. We have to be explicit about what are the initial and final states we're going to use, right? In these equations down here, this represents the initial velocity x component, and this is the final velocity x component. What does that mean? And I have to make sure that the acceleration really is constant all the way from initial to final. And then we start looking at what things are we given. There's a lot of symbols down here. Which ones of those symbols do we know? Which ones do we want to know? And then we start looking for kinematics equations that involve the thing we want to know. And even more so than in chapter 2, you're going to find that oftentimes it's not just a one and done. You're going to have to work and think, okay, here's an example problem that you saw in the video. Here's a pitcher who's releasing a ball horizontally, so initially throwing it horizontally, and then it falls on the way to home plate. That's probably not the way pitchers actually throw, but it was a good example to start with here. And you're given the initial speed. So I drew a little crude diagram. I decided where to put my axes and origin. I also decided that the initial is going to be when it was released, just after it leaves contact with the pitcher's hand. Final is going to be just when it's passing over home plate. And our goal is to find y final. That will represent how far it drops. And the idea is if you look down at these equations, you could say, well, I want to know y final. What has to do with those? Well, it's either sitting down here in the delta y, or it's sitting up here. And so if I look at this equation, I might say, I know everything in this equation except y final and t. So if I only knew t, I'd be done. I haven't used that distance from home plate to the pitcher's mound yet, the 18.4 meters. How am I going to use that? Well, I can plug it into this x versus t equation, and looking at all the detailed symbols in there, you'll see that the only thing you don't know in there is t. So we can use this equation to find t, substitute over here to find y final. In my coordinate system, y final is negative. If you're answering someone who says, how far does it drop, you usually wouldn't give a negative answer. So I would tend to just throw away the minus sign. I'm expecting a negative y final in my coordinate system, but I would tend to just answer as a positive number. Second example, and some of you asked about this in your reading response questions, so this one was in the video as well. Soccer ball is kicked from the field, and later on it comes back down to the field. We're supposed to, I didn't say ignore air resistance, but we're supposed to ignore air resistance here. I try to remember to say that explicitly in all these problems. Probably pretty realistic here, unless the soccer ball is going super fast. And so we're told not only that it goes from the field to the field at some later time, but we're told it's kicked at 22 meters per second, right at that kick point, and it's going at an angle of 40 degrees above the horizontal. So if I drew a line tangent to this parabola here, that line would make an angle of 40 degrees right there. And in order to solve this problem, we've got to figure out what the initial x and y velocity components are. We'll do this today in several example problems. And we can do that by looking at this diagram up here. I'm drawing, roughly this angle is supposed to be 40 degrees right there where I'm pointing at in that right triangle. This vector is of length 22 meters per second. That's what the speed being 22 means, is that the velocity vector has length 22 meters per second. The x and y components, Vx0 and Vy0, are defined by making the other two sides of this triangle. And the question is, given that I know this angle, I didn't draw it in there, and the length of the hypotenuse, how do I find those two sides? That's what we did at the beginning of chapter 3 with those right triangles, right? And through the angle or across the angle, or you could use your SOHCAHTOA depending on how you do it, right? But I know the hypotenuse and I know an angle, so I can figure out these two sides. It's 22 cosine 40 and 22 sine 40 for the x and y components in this particular case. And then I go and look at the kinematics equations, choose some. In this particular example, it happened to be the same two that we needed in the other example, but it's obviously not always going to be that way. We'll see, we'll use all the equations today. Okay, any questions on that process? I'm going to do 3 more reading response questions, and then we'll get into some practice problems. These ones are starting to have to do with ballistic motion or projectile motion. Will we always be allowed to assume that for an object thrown up into the air, allowed to reach its highest point and come back down, has a total time that can be split into 2 halves? Can we assume the time up will always equal the time down to the ground? And the answer is yes. We should justify it once. It seems reasonable that it would be that way. Just to give myself a chance to practice with this, I'm just going to unshare the screen for the purpose of nobody who's on Zoom. We've already said that if I plot, say, y as a function of time, that shape of that graph is given by this relationship, y equals y0 plus vy0 t plus 1/2 ay t squared. And if I focus just on the t's as being like my x coordinate, because we're plotting it on the horizontal, and this y as being my y coordinate, this is like y as a function of x is a quadratic function of x, and it's a parabola. So it's a perfect parabola. We know what parabolas look like, and we know since this thing's accelerating downward, if we're talking about projectile motion, it's going to be a perfect parabola like that. And one property we know about parabolas is that if you, I may not have drawn it perfectly, but if you look at the vertex up there, parabolas are always completely left-right symmetric. And that means that this distance, which is really an amount of time, it's on the time axis, is exactly equal to this distance in time. And that means the time it takes to get to the top is exactly the same amount of time as it takes to get down. So that's a justification that if somebody says, oh, this object's, this is the ground and this object's in the air for 10 seconds, how long does it take to get to the highest point? Oh, that's easy, it's 5. I don't have to think about it, but that's the justification. Perfect parabola is always left-right symmetric. I know by looking at it that this is not a parabola because it's not sort of drawn in a skewed way. It's not left-right symmetric with respect to the vertex. Okay. It's also true, I should mention, and I think somebody else mentioned this in the reading responses, that if I plot the path of the object, so this isn't the path of the object, this is just the y coordinate as a function of time, but if I want to see the path of the object, what shape it takes through space, that would be drawing the locus of points that it takes as it goes through the air. Y as a function of x, not as a function of t. It's a path in xy space. That's also a perfect parabola. You can justify that by using, again, we're using the fact that this maybe is minus 9.8. And when I do the corresponding x equation, bx0t plus 1/2 ax t squared, that ax is 0. It's not accelerating in the horizontal direction. It's only accelerating in the vertical direction. So if you really wanted to justify that that's a perfect parabola, solve for t here. X is a linear function of t. If I solve for t, trust me, t will be a linear function of x. And if I plug that linear function of x in, substitute in for t here and here, square the whole thing out, when the smoke clears, you'll find that y is a quadratic function of x as well. So this is a perfect parabola. So if you're looking for, you know, if I draw the locus of that soccer ball, right, and I say, this is 40 meters, then you know the distance it's traveled horizontally on the way to its highest point is exactly 20 meters because it's a perfect parabola. That's a useful time-saving thing that I don't want to have to reprove every time. But those both are perfect parabolas. Okay, let's screen share again. I don't understand how our initial velocity is always in regards to when it is resting on top of a table, or it hasn't started falling downwards yet, but isn't gravity always in effect? Like we are not feeling a downwards acceleration of 9.8 meters. Are we not feeling a downward acceleration of 9.8 meters per second all the time? I think this is related to that previous question that I said, where I'm a body. I can't have two accelerations at the same time. So right now, I'm not accelerating. I can feel the effect of the gravitational force because my body kind of feels heavy right now, right? But it's not the only force on me. The floor is pushing up, and we'll find a body can have lots of forces on it, but it only has one acceleration, assuming it's moving as a rigid unit. So all the pieces are moving together. And again, that will make more sense in chapter 4, where we talk about the relationship between forces and acceleration. And we investigate a lot of forces. Final question, and we'll do some problem solving. Would a tremendous amount of spin on a ball cause a significant change in the object's projectile motion? For example, baseballs that are hit with backspin. So if a baseball is going like this, it's going to travel farther in the air. It sort of gets some lift from it. As opposed to if you hit a baseball with forward spin like this, it tends to just fall back down to the ground even faster than it would if there were no spin on it. And also, is it possible to calculate the motion of a ball that's thrown with a sideways spin, you know, sort of corkscrewing through the air like that? The answer is yes, it is, but it's extremely complicated. So we won't address those problems in Physics 110. They're just really complicated. Most of the time, you calculate the path of these balls when air resistance, and in this case, it really is resistance. The air is resisting the spinning of the ball. But it's complicated because the speed of the surface of the ball relative to the air surrounding it might be bigger on certain sides of the ball and smaller on other sides of the ball. And it's just a complicated problem. So people generally solve those on computers and compute what the path is as a function of time. It's not something we're going to do in this class. You wouldn't do it in an elementary physics class. You might do it in an advanced physics class, but you would need a computer to do it. It's not something you could just do on your paper. All right. Other questions you can think of while I'm passing these out? Let's start with problem 1 on here. I tried to organize these 4 problems, which each have multiple parts, so I think this is going to take us a while to get through this worksheet. But they're all good problems. I tried to organize them from roughly the most elementary to things that seem more difficult, although for the difficult ones, you'll see examples of that level of difficulty in the homework for sure, if I remember correctly. So here we've got a ball rolling on a horizontal table with a given initial speed, and it goes off the edge of the table. That's kind of like that image I was showing on the slides. And it falls to the floor. And we're told how far from the edge to the floor, and we're supposed to answer several questions about it. How much time does it take to reach the floor? How far does it move horizontally speaking? And now I've passed out all my copies, so I don't know what the third one is. But what's the ball's speed just before it hits the floor? So why don't you just to sort of throw ourselves right into it, the tools we're looking at, and maybe I should back up here to the point where I've got the kinematics equations all listed, just so we have some place to look at them. There they are up on the screen. See if you can figure out how to look at those. Let's just spend a couple of minutes to figure out how much time it's in the air from when it leaves the ledge till just before it hits the floor, and how far it goes horizontally as measured on the floor, from the point just below where it leaves the ledge to the point where it hits the floor. If we measure horizontally with a tape measure, what would that be? All right, let's just come together and talk about parts A and B, and then I'll ask you, probably most of you haven't had a chance to get to see yet, but I'll just ask you about how we might proceed there. The first thing you always want to do in these problems is draw yourself a little cartoon of what the motion looks like. So in this case, I've drawn the table with the ball just about to leave the edge. That's right after it leaves the edge and about to hit the floor. I've drawn in the distance that I know that it's 1.6 meters for the bottom of the ball to get from the top of the table surface to the floor. That's how far it falls, is 1.6 meters. And we know its initial speed, which is in the horizontal direction. It's traveling horizontally initially. So it's not like it immediately changes as soon as it leaves contact with the edge. There's a moment when it's still going horizontally, and then it starts to fall vertically too, but it doesn't change instantly. So the first thing I got to do is decide what initial and final are, and I am interested in finding this, in part B, this horizontal distance from right below where it leaves contact to where it hits the floor. And in part A, we're interested in how long this takes going from there to there. So it seems, reasonable to take the initial to be just after it leaves the edge and the final to be just before it hits the floor. And it's in free fall that whole time. So that's good. We can use our kinematics equations with little g, or 9.8, thrown in the correct way. Second thing I need to do is define my coordinate system. Right? Because I don't know what x or vx even means if I don't have an x-axis. And there's several ways you could do it that make sense. In my solution that I have written out, I chose the point right below where the ball leaves the edge to be the origin. And I chose plus y to be up and plus x to be along the direction it's going. And in that case, I can fill in a lot of information. I know that the initial x velocity component is what? It's 1.3 because it's all moving. This is right when it leaves the edge. This is what its velocity vector looks like. It's all in the x direction. So it's 1.3 in SI units. The initial y velocity component is 0. The x acceleration is 0. The y acceleration is minus 9.8 because I chose plus y to be up. It's fine if you chose plus y to be down. It's also fine if you chose your coordinate system to be up here where the ball was initially. It's going to affect some of the numbers that I put in. I might say my y initial is going to be 1.6 meters in this coordinate system, right? It starts out at y equals 1.6, and my y final is going to be 0. If you chose your coordinate system to be up here, you would say y initial is 0, and y final would be what? If I chose my coordinate system to be up here, what would the final y be? Yes, negative 1.6, right? Because you'd be down below the x-axis by 1.6 meters when you got here to the final state. So you've got to be careful with all those minus signs. There's no necessarily right way to choose that coordinate system. I wouldn't want to put it in some random location, and certainly not with a random orientation. That would just be making my life a living hell doing this problem when I could have made it much easier by orienting them horizontally and vertically, because I know which direction the acceleration is. All right, now that we've got everything sort of laid out, I guess I could also put my initial x here is 0. Everybody okay with that? My initial y is plus 1.6 in my coordinate system. I'm just leaving out the units because I'm going to put all SI units in, and therefore I know we'll get all SI units out. That's our dimensionally balanced. Then we come over to these equations, and we want to find t. Well, that's sort of unfortunate because I forgot to stop sharing my screen. Boy, it's going to take a lot of practice on my part to learn to go back and forth. There are 4 equations that have t's in them, so that seems like too many choices. Where can we go? Who's got a suggestion for which one might help me get to solve for t the fastest? That's what we're asked for in A. I could do that. So that sounds like a two-step problem. Is there any way I could do it in just one step? Was anyone successful with that? Yes. Yes, that one will actually get you there in one step. So let's just look at all four of them that have t's in them, right? In this case, this is not going to help. Why is this equation totally useless for me? Well, I do know everything except t, but part of knowing everything is knowing that ax is 0. And if I plug ax equals 0 in there, the t disappears. So I'm not going to get, all I'm going to get is that vx final equals vx initial. So it doesn't slow down along the x direction. That doesn't help me find t. So that one's no good. The problem with this one right here is I know vx0, I know x0, I want to know t. Ax is 0, so that part goes away, but I still have a t in here. Hey, that looks promising, but I don't know x final. X final is the answer to part B, right? What x coordinate is it at over here? So that one is not a one-step kind of problem. I would still have to do more work. I also don't know what the y component of the velocity is right before it hits the floor, right? It started going down, and I don't know what its final y velocity is. So there is a t in here, but I don't know what this vy final is. So this one seems hopeful. Let's write it down again over here and just work on it. Part of this is just experience with practice doing these kinds of problems and seeing what works and what doesn't. Okay, there's the one we've chosen. And let's just make sure that we know everything except t. This is my y final. What's y final? 0 in my coordinate system. Y initial was 1.6, right? What's vy initial? 0. It was all going along x when it left the table. It wasn't moving along y initially at all. That changes later on, but that term is 0. 1/2 ay is minus 9.8 in my coordinate system, and then I've got a t squared, and that's not so bad. I put this over here with a minus sign, then cancel the minus signs, then multiply by 2, then divide by 9.8, and then take the square root to get t equals 0.571 seconds. Right? I've put in all SI units, so then when I get the result here, I know, what did I say? 0.571 seconds. I know that the correct unit to put on it is seconds, as we put all SI units in. That's kind of nice. All right, I'm not saying there aren't other ways to do it. You could find vy final, and then you could find vy final by using this equation, because I know how far it went down in between initial and final, and I know ay final, and I know vy initial is 0, so I could find vy final and then substitute into this one to get t. But that's a two-step problem, so it seems a little bit better this way, given that we didn't really have to solve a quadratic equation there. That seems better. More questions on A. And so then B is asking, how far does it travel, horizontally speaking, between initial and final? So we want, in my coordinate system, x final, because x initial is 0, right? So x final will just, if I know what this x coordinate is, that will mean how far it went, because x initial is 0. All right, again, I'm going to look at my equations. There may be more than one way to go. Who has a suggestion for which one to grab first? I'm hoping I can do one and done if that works. That's not always going to work. In fact, you should consider yourself very lucky if you can find just one equation that gives you the answer. But maybe this is our first problem. The second x one, yes, that's the quadratic x one. The nice thing is we know this t now, so that t squared doesn't worry me so much. X equals x initial plus vx initial t plus 1/2 ax t squared. Hey, that's kind of nice. Ax is 0. Don't plug in 9.8 for ax. It's easy to get mixed up with those, but you got to keep your head straight and know Am I talking about x or y, or horizontal or vertical? And here x is horizontal, so it's not accelerating horizontally speaking. So x final is what I want, and this is telling me hopefully how to calculate it. X initial is 0 in my coordinate system. Vx0 was 1.3. And the time it takes between initial and final we just found is 0.571 in SI units. So hey, that's really easy now. I just multiply those numbers together. 0.743 meters I have. Again, I'm just throwing on the SI unit at the end because I know I put everything in SI units, so I'm going to get SI units out. Questions on A or B? Okay, you will get a lot more practice doing this in the homework, I promise you, but we'll do a lot more practice today. All right, C, what is the ball's speed just before it hits the floor? How fast is it going right here before it hits the floor? Well, is it going at 1.3 meters per second? No. Is it going faster or slower than 1.3 meters per second when it hits the floor? It's going to be going faster because, well, one way to look at it is, since this last term in that x versus t equation is 0, that means, well, I guess that's not what I wanted to look at. This equation, since ax is 0, that tells me that Vx final is Vx initial. So the x velocity doesn't change the whole way through this motion. It's progressing along the x coordinate at the same rate the whole way through. That's not true for the y coordinate, y velocity component. The y velocity component starts out at 0, but then it gets more and more negative as time goes on. So I'm going to have not only that 1.3 x component plus an additional y component, and I've got to use the square root of the sum of the squares to combine them together. So in C, we are going to say the speed, that final speed, I don't know why that's equal, is equal to the square root of Vx final squared plus Vy final squared. And I just made the argument, but tell me again, is everybody okay with this number here being the same as the initial? It's the same as the initial by virtue of this equation because ax is 0. It's just telling you, hey, your x velocity doesn't change if you're not accelerating. That's what not accelerating means. You have a constant velocity, and it's not constant velocity in this case, but the x component of the velocity is constant. So all we need to do to solve this problem, or I've reduced it down to, if I only knew Vy, I could throw it in there and I get the answer. How can I get Vy? Vy final. Well, I come over here and I say, which equations have a Vy final? Hey, this one does. Do I know everything on the right-hand side? What's Vy initial? 0. Ay, minus 9.8. The t, we found that in A. That means the time between initial and final, so we could use this one. The other one that has a Vy final in it is the third one. We could use that one too, I believe. We know how far it goes, what its y displacement is in between initial and final, and that is y final minus y initial is going to be minus 1.6. So this thing is minus 1.6. This is minus 9.8. This again is 0, so I could solve with the square root there. Either one of those would work, but maybe it seems like the first one is simpler. So Vy is equal to Vy0 plus Ayt. That's equal to, it starts out with no y velocity. The Ay is minus 9.8. And the t is what we found in A, 0.571. Okay, so that means Vy final is negative. Yeah, it was going down and my plus y is up. That makes sense. That number, by the way, is minus 5.6 meters per second. And therefore, I can do a 1.3 squared plus a minus sign when you square it just goes away. So here I'm just going to do 5.6 squared. And that number is 5.75 according to my notes. Okay, we'll see this is a kind of plain vanilla, but definitely on the easy end of the spectrum of these projectile motion or ballistic motion kinds of problems. All right. I want to go on now to problem 2, and I want to give you some time to work on it first. This one is a little bit more involved than the previous one, and it's got 4 parts, but let's just start concentrating on A and B. Actually, it's got 5 parts, I see. Let's start out with A and B to begin with. A walnut, I used to live, so I live in Lexington now, but I lived in a house in Danville, and we had a walnut tree. Now, when you buy a house, don't buy a house with a walnut tree, because walnut trees make a huge mess. That, when you buy walnuts at the store, they don't have the rind on them. The rind is this messy thing, and it just gets black everywhere. And when you drive over them with your car, it would shoot the walnuts out. And a previous owner of our house had actually broken the neighbor's window by shooting a walnut through it. That's what the neighbor said. In any case, this actually happens. Walnuts kicked up from the horizontal street by a passing truck's tire. It leaves the ground at an angle of 28 degrees above the horizontal direction at a speed of 9.1 meters per second. Ignore air resistance. For how much time is the walnut in the air? And how far does the walnut land from its launch point? That sounds rather similar. The questions that are being asked rather similar to the previous one. So let's see if we can get to those. And let's see, I was going to go here just as a reminder that it might be worth your while to figure out what Vx0 and y0 are using that kind of idea, right? We know how fast it was going and at what angle. What does that mean the initial x velocity component and y velocity component are in this case? So try to do A and B. You can even, if you're fast at this kind of stuff, get into C, but at some point in the middle of it, I'll bring us back together to finish it up. And I should say Katie has to leave early every Wednesday, so that's just going to be a regular occurrence throughout the semester. If you're having trouble getting started, feel free to call me over. Yes. Yeah, I don't either. I mean, we might be able to calculate it some other way, but I don't know necessarily what it is. Now, you may have some intuition that, and we can actually prove this at some point later on if you like, that if something is shot up with a certain speed, and we know its initial x and y velocity components, then if it lands at the same height that it left at, its x velocity component won't change, and it seems like its y velocity component would just reverse. It was going up to begin with, and now it's down. And that, in fact, is true. And you can justify that to yourself with one of the other kinematics equations that will tell you. In other words, what I'm saying is, if you end at the same y coordinate that you start with, this term is 0, and that says that Vy final squared is equal to Vy initial squared, which means Vy final is plus or minus Vy initial. And in this case, if you're talking about that one over there where we know it's the negative of the original one, if it was going up to begin with, it's going down. So I guess you could use that if you wanted to start that way. I started with the y versus t equation because it seemed just more directly to get you there. Yeah.
Time versus should we divide that?
Yes, you can by the justification that we gave earlier that y versus t is actually a perfect parabola, which means if you know how much time it takes to get from one height to the same height later on, then the amount of time it takes to get to the maximum height is exactly half that time. And you're free to use that without justification now that we've justified it once. I put my numerical answers up there just so you have something to check against and puzzle over if you're not agreeing. It's always possible that I made a calculational error, but at least it's something to check against. Okay, let's start part A together because it is a little bit more complicated than what we did in the previous problem, even though I'm going to kind of start from the same place. The algebra is just a little bit more complicated. But before I even get there, if I'm going to apply the kinematics equations, I need to be definite about my coordinate system. Here, there are less reasonable choices. I mean, it seems like the only really reasonable choice is to make x and y horizontal and vertical and make the point where the walnut leaves the ground be the origin. You don't have to choose that. Could be where it lands, but I don't know. You could choose plus y down. It doesn't really matter one way or the other. And then, so I know in that case, x0 and y0 are both 0, of course. I don't know vx0 or vy0, but I can get those by that right triangle calculation. In other words, here's a vector whose length is 9.1. That's the initial velocity vector. By definition, the x and y components mean in going from tail to tip, how far do I move along x? That's vx0. And how far do I move along y to get to the tip? That's vy0. And so this hypotenuse is length 9.1. This angle is 28 degrees. And that means that, well, my thing of starting with a hypotenuse, what do I do to get to this side? Oh, I pivot through the angle. I like that, and I like the cosine for some reason. Vx0 equals 9.1 cosine 28. Vy0 is 9.1 times the sine of 28 degrees, and those numbers will be useful for us. So they're 8.035 meters per second and 4.272. Okay, so that's one reason this problem is just a little bit more complicated than the other one. It started off going horizontally, so we didn't have to resolve a vector into components, but here we do. All right, so I know, and I know my AX is 0, AY is minus 9.8, so we're ready to start going. What we want in A is T for initial being here, and final being here. I mean, just before it hits the ground and just after it leaves the ground. So those are my initial and final. And I'm ready to go in A to find T. And, well, I don't know anything about how far it goes. And we'll also find that, using the Vx versus T equation doesn't really help much because AX is 0, so it reduces to something not helpful. What I do know, and it's not immediately apparent from the picture, but it makes sense once you realize it, I know the final y position. It's the same as the initial. They're both 0. Starts at y equals 0 and ends at y equals 0. And I want to find T. So this kind of seems hopeful. Let's write it down and just try to plug stuff in and see if there are any unknowns left except T. Y equals y0 plus vy0 t plus 1/2 ay t squared. It ends at y equals 0 in my coordinate system. It starts at y equals 0 in my coordinate system. Its initial y velocity is 4.272. There's still a t next to it. That's my unknown. Plus, well, let's see, AY is minus 9.8. When you divide 9.8 by 2, you get 4.9. So with the minus sign, that would be this 1/2 AY is the same thing as minus 4.9. And there's still a t squared next to it. And if you were feeling really energetic and lucky, you might throw this in the quadratic formula, but you don't need to use the quadratic formula here. How do I avoid doing that? What's the method that your freshman high school math teacher would be really excited about? Or at least when I was a freshman in high school. I don't know when. Maybe you do that in 8th grade now. You do something called factoring. Right? There's a common factor of t on the right-hand side. So this reduces down to 0 equals, I can factor out a t. What's left is 4.272 minus 4.9, and there's still one factor of t left in there. So if I distributed, you could see it's the same thing. And then you use that old fact about the product of things being 0. There's no way two non-zero numbers could be multiplied together and give a 0. Either one of them's got to be 0 or the other one's got to be 0 if they're going to multiply to 0. Because if you multiply two non-zero numbers, you get a non-zero number. So that means at this point I can conclude that either the first factor is 0, t is 0, or the second factor is 0, which is, well, I won't put the parentheses in there, 4.272 minus 4.9 t equals 0. Either the first factor is 0 or the second factor is 0. Well, the first factor being 0 corresponds to it saying, well, I want the final y and the initial y to be 0. Well, if I take the final and the initial to be at the same point, that would you'd trivially solve what I'm looking for, but that's not the one I'm looking for. I'm looking for the other time at which y is equal to 0. That must correspond to this equation over here. And I can easily solve for t there, a nice linear equation. I get 0.8719 seconds. Oh, I've got it written up there, 0.8719 seconds. I'm just not really worrying too much about significant digits. I guess I kept an extra one in case I wanted to use it in a later calculation, which I will, so I kept a little bit of extra accuracy rather than rounding to 3. Questions on A? 0.60? 0.628. And first of all, let's vote on it and see. I'm not going to say that's the end of the conversation. Did divide, okay. Okay, well that's A. So now we know the time. We might be able to use that later on. How far does the walnut land from its launch point? Well, again, it seems reasonable to call this initial and this final, so I'm going to keep those conventions. I can change them as I go to different parts, but in B, I'm going to keep the same initial and final. And rephrased in terms of my coordinate system, I would like to know x final, which is just called x in Giancali's notation, right? So I'm looking for that x, which represents x final. And in this case, well, I've really got two choices. This one's not going to help me because ax is 0 and it's multiplying x final. So the only real choice that has an x final in it is that quadratic equation. It's not really quadratic because the quadratic term goes to 0. X equals x0 plus vx0 t plus 1/2 ax t squared. Just for your benefit, I always write down the generic version of the equation first so that you know where we're starting, and then we substitute underneath. You don't have to do that, although you might find it helpful. So in this case, we want x final. X initial is 0. Vx initial we already found, 8.035. T we just found in between that initial and final was 0.8719. And fortunately, because I'm lazy, the last term is 0 because ax is 0. And so I just need to multiply those together. So that was easy once we did all the work for part A, 7.01 meters. Questions on that one? Let's say A is by far the harder part there. Now that we got that time, B is pretty easy. And C, maybe some of you got into C, what's the maximum height above the ground the walnut reaches? Now in C, why might I want to change my mind about what initial and final mean? Yeah, we want to know something about where it is here, and that final there isn't going to help me. So maybe I will now, for the purposes of C, you could just in your head, but at first it's good to be very explicit about it and maybe write it down. I certainly do that when I write my solutions. I'm going to take final up there, and we want to know, if we want to know how high it is above the ground, right? That's what was asked. We want to know, with this being final, what is y final, right? So where would you go in terms of kinematics equations there? Yeah, you could use actually either the second one or the third one. They both have a y final in them. In this case, we don't necessarily know t between 0 and the final state, but we just argued that because this y versus t is a perfect parabola, the time to get to the maximum height is half of the time it takes to get down to the initial height. Right? That was one of the arguments I made in the context of the reading responses. So I could get y final, for final meaning the maximum state, by plugging in half of the time that we just calculated in A for t here. That's one way to do it. Or I could use 3 just to mix it up a little bit. Let's use the third equation. Vy final squared equals Vy initial squared plus 2ay delta y. And in this case, delta y represents how much you go along the y direction in between initial and final. That's what I really want to find here. So that's my unknown. And let's just try to plug in what we know about all the other things. What's Vy final? If we're at the very highest point, it's 0 because the object is actually moving momentarily horizontally, which means it has a non-zero x velocity component, but its y velocity component at the very highest point is 0. So this is 0 squared. Vy 0, we already calculated, 4.272. Don't forget the square that goes on there. Plus 2 times minus 9.8 times delta y. So I can just solve for that delta y in my calculator. And the number's up there on the right, 0.931 meters. Sorry. Yeah, 0.931 meters. I thought it was a 9.1, but yes, 0.931. So it doesn't even make it up a meter. I guess it was shot much more horizontally. The angles, this does not look like a 28-degree angle. This looks more like a 70-degree angle or something like that. So my drawing's a little bit misleading there. Okay. What speed? Okay, D is easy. What speed does it have at this maximum height? I can do that without even getting out my calculator. What speed does it have at its maximum height? I've already done all the work I need. Say what was that? Yeah, it's the x velocity, the initial x velocity doesn't change, right? So at the very highest point, I guess I shouldn't have moved this over so quickly. At the very highest point, it's moving just like that, right? The velocity is always tangent to its path. I've drawn its path there with the dash curve. So at the very highest point, this is, if that's final, this would be my v, well, this would be my v final as a vector. And its x velocity component is non-zero. And in fact, it's equal to its initial x velocity component. Again, you can justify that in terms of this equation over here. Ax is 0, so this term goes away. And that means Vx final is going to be Vx initial, or even, maybe even more simply here. If Ax is 0, Vx final is equal to Vx initial. That means its x velocity component doesn't change. And I can see from the picture, by definition at the highest point, Vy final is 0 at that highest point. So when I plug in, just, you don't necessarily have to write this down, but V final is equal to the square root of Vx final squared plus Vy final squared. And Vx final is Vx initial, we just said, and that was 8.035 squared. And Vy final is 0. And when you take the square root of something squared, you get that same number back. So if you have your head screwed on really straight when you're thinking about this, you don't even have to write anything down. You could just write 8.035 meters per second. Questions on that? Whew, okay, let's go on to E now. At what height above ground level does the walnut have a speed of 8.5 meters per second? Well, it's not at the highest point. At the highest point, it has less than that speed, very close to 8. We're looking for 8.5. So it's probably slowing down as it goes up. Some height below that, it would have that speed. Initially, its speed was 9.1. So it's something above the ground, but less than the highest point. I want to know how high above the ground is it having that specific speed? Anybody have a suggestion for where to begin? The third one for the x or the y? For the y, yeah. So that would allow me, if here we're talking about, by definition, I have to know what final is. I'm going to change my mind again about final and just say final is whenever it gets to that height at which it has that speed, right? Part of what I need to know is, well, I want to know this y final. And if I only knew what Vy final was, it seems like I might be able to solve for y final. Okay, so let me try to draw a picture just to make sure it's clear. The walnut, again, not a realistic drawing here, but the walnut goes up and down. And here is where its speed is 8.5 meters per second. Right, it's still partially heading up. That's going to be my final. Final, and my initial is still going to be here. And the idea is, if I take that third y equation, well, we could have chosen it on this side as well, and we'll find out it's at exactly the same height. In other words, going back over here, well, the x velocity component doesn't change. And so the question is, when does it have exactly the right y velocity component to give it a speed of 8.5? And when the final height is equal to the initial height, this term goes to 0, and that means the y velocity component just changes sign, which wouldn't change the speed. So another way to say that is, at the same height on this parabola, there and there, or there and there, or there and there, it has the same speed at those locations. The x velocity component hasn't changed, and the y velocity component has just switched signs, which means when you take the square root of the sum of the squares of them, it doesn't change the number. You could, yeah. Especially given that we found out some stuff about the top already now, right? Doesn't really matter. I think it's just as easy one way or the other, and there's often more than one way to get the answer that's just as easy. But let's continue with the original suggestion, which was to use that other one. So I'm going to take that to be final, and I'm going to say, I know how to calculate the final speed, which I want to be 8.5, if I remember correctly. 8.5 better be the square root of Vx final squared. And Vx final, we said, we already figured out that's Vx initial. So 8.035 squared plus whatever Vy final is squared. And I don't know what Vy final is. But that's an equation that only has a Vy final in it. And so I could use it to solve for, rather than knowing what the final speed is, I'm saying that's equivalent to knowing that Vy final is, where am I? 2.773 meters per second. So if I could only find out where Vy final is, at what height Vy final is 2.773 meters per second, I'd be done. And now that's something, you know, I don't see any just plain V's in here, but I do see Vy's and Vx's. So the suggestion is, now that I know what Vy final is, I know what Vy initial is. We calculated that at the beginning. I know what Ay is. I know what Y0 is. So the only unknown in here is Y final. So let's plug in there with that Vy final. So that's the hardest part. You're given a speed here, and you really want Vy final. The problem would have been more straightforward if it were asked in terms of Vy final. Vy final squared equals Vy initial squared plus 2Ay delta y. But we'll write that as y final minus 0. And Vy final is 2.773 squared. Vy initial was 4.272. Don't forget to square it. Plus 2 minus 9.8 times y, and solve for y. And y is 0.5388 meters. Okay, so this problem, not only does it have more parts than the first one, it's just requires that you really be willing to jump in and say, what do I need to know? Let me just write down something that might get me to the thing I want to know, and then figure out what else I need to know to get at that. So in this case, I wanted a height. I was given a v, but there's no v's that appear over there. So I translated that into a vy and then found an equation that would give me a y final. That takes a lot of practice. So this is sort of, maybe a medium level problem. And I would say the next two, and I kind of want to just take a break for a couple of minutes to stretch a little bit before we go on to the last two problems. Any more questions on this one? All right, stretch out for a minute. I know these class periods are long. I don't have any pets unless you include my 3 kids that I have. I don't know if that's condescending, but yes, I have 8, 10, and 12 are their ages now, so we're very busy. They're all learning from home, of course, right now because the public schools aren't in session. So
The tip my mom wanted to share with all of my professors, because I was homeschooled all through grade school, is the butcher paper is a lifesaver. So it's the big rolls of paper that you can put across the wall, and they can use it as temporary whiteboards to either draw, do stuff, homework. I'm just like, okay, Mom.
Sounds good. Yeah. I mean, I would almost think a whiteboard might be
Either a whiteboard
just as good.
The hard thing with a whiteboard, because my mom learned the hard way with my sister, she's also homeschooled, is that whiteboard markers and walls sometimes are the best. Because like switching between whiteboard.
Yeah.
Like your kids are old enough.
You need a thick frame. Yeah. Okay, well, I'm not sure if everyone's back yet, but let's just look at a couple of these reading response questions again to kind of clear the air, because I know this is kind of intense problem solving. The last two problems are what I would consider to be at the harder end of the spectrum. And normally I don't do those right when we're doing examples in class, but you're going to see a couple on the homework that are as hard as these ones, and I figured, well, I don't want to throw you into the homework without having tried them. But let's look at some of the reading responses first. When looking at projectile motion, in what ways would the process of something being thrown differ from the process taken while it is in the air and before it lands? So when it's in the air and before it lands, presumably we can ignore air resistance and we can use our acceleration as constant, as projectile motion. So with the whole process we've been doing. When it's being thrown, I mean, I'm assuming that's when I'm pushing on it and throwing it up in the air. I don't really know what the acceleration is then, so I don't have a process by which I can solve it. Now, we will find in chapter 4 that if I knew everything about the forces that were on it, so that means gravity is still a force on it while I'm throwing it up, but my hand's an additional force. And if we knew both those forces as a function of time, because probably my hand force is changing, the direction's certainly changing if I underhand toss it up like that, then in principle, we could solve for the acceleration, figure out the acceleration, and maybe get the position as a function of time while my hand is going up in an arc. But it would be a very complicated problem because the acceleration is not constant. So we're not going to address those kinds of problems. So you'd have to make a lot of assumptions about it for us to do it here. That doesn't mean that everything's going to be constant acceleration for us. We will definitely do stuff that's not constant acceleration, but still, we don't want to do stuff that requires us to do computer modeling just to even get some sort of approximate answer. The example on page 61 involves the use of the quadratic formula in kinematics, in which both the positive and negative versions of the solution were both used. Is this common for both solutions of a quadratic to be relevant in 2D? Well, it depends. Sometimes both solutions are quadratic. I might have a problem where, you know, maybe it's the walnut problem, right? The walnut is kicked up from the ground and it comes back down later on, and we call this t equals 0. And I might say, how much time elapses before it reaches a height of 4 meters? And maybe the maximum height is 5 meters. So here it is at 4 meters up. Here it is again later on at 4 meters up. So at what times is it at a height of 4 meters? Well, there's 2 times. An earlier time, and then later on I had to wait longer to get to that one. And so you might say, oh, well, I know y equals y0 plus by0, t plus 1/2 ay t squared. Y initial was 0, y final is 4. You know, I've got my vy initial t and a quadratic term. So I would have an equation that involved t squareds here. It would have 2 solutions to it. And in this case, both of them are relevant, right? They would both kind of be answers to the question. There are 2 times. But if I had that problem we started off with the ledge, and this thing just goes like that, and I say, at what, you know, suppose this is 6 meters, and I say, at what time, how much time do I have to wait for it to reach a height of 4 meters? Well, there's only going to be one time on the way down. When I use that same quadratic formula, it's going to give me the time here, which would be a positive time. It's also going to give me a negative time that corresponds to, as if this thing was all in free fall the whole time, at what time would it have been here? Now, it wasn't in free fall the whole time, so that answer doesn't make any sense for us, but that's what the meaning would be. If somehow it had been in free fall and just happened to reach its highest point, then there would be a negative time. If I called this t equals 0, this would be a negative time. That would be a positive time. So sometimes they're relevant, sometimes not. Problem 3.8 defines horizontal range. Is this range equivalent to the x component of the displacement vector? Why can't the range formula be used for a scenario where the final y displacement is not 0? Well, just because that assumption, the range equation is telling you, if you know the initial speed and angle, like we did in the walnut problem, it immediately tells you how to calculate this. I think it calls it capital R, how far it goes horizontally. And, you know, if it landed on a ledge up there, well, it wouldn't be as far. But that assumption of starting and ending at the same height was used in the derivation of the range equation. So you can't use it. The point, part of the point of me putting this on here was to remind me to say that I'm generally not going to use the range equation. You can use it, but I'm going to always start with the kinematics equations and try to get to the point where we might use it. And we'll see in this third example, there is a problem where it starts and ends at a different height, and we can still figure out how far it goes horizontally. Final question. In the video, it was mentioned that during projectile motion, gravity acts as constant acceleration. But then it was mentioned that when an object is in contact with a Canahan table, the object's acceleration is no longer constant, so we're not supposed to include that time frame. I just wondered if not including these times would significantly impact the change in time you put into your equation. Or is time so insignificant that as of right now, we ignore it? Yes, so in this one where the ball was leaving the table, I would say there's an insignificant amount of time from the point where it was just barely touching the table to just 1 nanometer separation between it and the table. I mean, that would be a really small period of time. And when it was 1 nanometer above the ground and when it touched the ground. So, you know, we're just ignoring that small amount of time. In fact, we're assuming that amount of time is 0. But we're just going to assume it's in free fall all the way until it hits the ground. Really, it's right before it hits the ground, but we're going to assume that those are essentially the same time. Okay, let's move onward to the next problem, which involves a football being thrown. You know, all of these, we're not going to use the shape of the football or anything like that. But I want to start this question together because it's a little bit more confusing. It's the first time you've seen this kind of problem, you probably would run into a roadblock. Football is thrown from a height of 2.3 meters above the ground at an angle of 38 degrees above the horizontal. So let's try to draw the trajectory of the football. It's parabolic. It's in free fall for a while. We're going to ignore air resistance. So here's where it's released from the person's hand. This is supposed to be 2.3 meters. Maybe that's a little bit high. I'm not really sure. And this angle relative to the horizontal right there is 38 degrees. We are not told its initial speed in this case, but what we are told is that it travels a horizontal distance of 22 meters. In other words, if we measure from the point just below the release to where it hits the ground, that distance is 22 meters. And in A, at least, we're supposed to find the time. Sounds like a popular thing to ask for. Okay. So I better decide on some coordinate axes, of course. And it seems like if we want the total time it's in the air, it seems reasonable to take this to be the initial and this to be the final, at least for part A, right? Coordinate axes, what did I choose in here? I chose them to be at the point on the ground below where it was released. You could have chosen them up there. You could choose plus y downward if you really wanted to, but I chose plus x there, plus y there. So I know I can figure out let's just write it down. Initial x is 0. Initial y is 2.3 in my coordinate system, right? Initial Vx 0, the initial x component. Well, I don't know that, and I don't know Vy 0. I do know the angle, but I don't know the speed it was released at, so I can't calculate that right away. And I can't remember if that's going to go into something in part B. So I don't really know those right away. But I do know the acceleration. Ax is 0, Ay is minus 9.8. And I want to know t. And when I look at this diagram, well, I know 2 things I can see. I know how far it moves in y in between initial and final. It goes down by 2.3 meters in between initial and final. And I know how far it moves in x in between initial and final. So it seems like at least trying, because I'm a little bit desperate here, trying to use the x versus t equation and maybe y versus t equation and see where we get with those might be a fruitful way to go. We'll see that it's not so straightforward. Let me just roll back to my versions of the kinematics equation just so I have something to point at. Okay, so x versus t, let's grab that first because I know x final, I know x initial. We're in A here. X final equals x initial plus vx initial t plus 1/2 ax t squared. Hey, that's kind of nice because my ax is 0. It's only accelerating along y. X final is 22. X initial is 0 in my coordinate system, right? I chose my axes to be just below the release point. Unfortunately, I don't know anything about Vx0. I'd like to use this 38 degrees because that's some information I know and is probably important. So in order to use it, what I'm going to do is put in a placeholder. I'm going to say, I don't know what speed it was released with, but I'm going to call that speed V0, the initial speed with which it's released. We were given that number in the last problem, but here, somewhat annoyingly, it wasn't given. So if that were the case, Vx0 would just be V0 times the cosine of 38 degrees. So I'm going to substitute that in. V0 times the cosine of 38 degrees plus 0, because Ax is 0. Oh, and I forgot my t here. That's Vx0 times t plus 0 in the last term. Where that came from again? I got lost. Okay, so we're starting with this equation, our old friend here, right? And the first thing I realized is that Ax is 0 because it's only accelerating downward the whole way through, right? X, I'm saying this is initial and this is final. My coordinates axis is down here, so x initial is 0. X final is 22, so I plug that in, right? X final is 22, x initial is 0. And then for Vx0, well, I'd like to be able to use that 38. It's a piece of information that I know. So I'm going to imagine I've got a vector here of length V0. I don't know what V0 is, the initial speed. It wasn't given in this problem. But I do know that it's at an angle of 38 degrees with respect to the horizontal. The thing that appears in this equation is Vx0. So if I know the length of the hypotenuse is V0, and I'm going through the angle, I multiply that V0 times the cosine of 38 degrees. I'm not claiming this is the obvious way to proceed, but you'll see it bears fruit as we go on. Sometimes you just have to say, well, I don't know that thing. I really wish I knew V0, but I don't know it, so I'll just kind of hold my breath and put in a placeholder. Maybe there will be a way to get rid of it later on, because we're not asked about it right here. Okay, it's also true that Vy0 I could write as V0 times the sine of 38 degrees. Okay, that's disappointing. I wanted t, but I've still got something I don't know in there. So I'm just going to put a little half box on that and say, let's hold on to it, because I still haven't used this 2.3 meters. There's still info I haven't used. So let's try to use that. And that seems like I would want to use Vy versus t, right? So going over here, the same thing for, sorry, not Vy, but just y versus t, because I know y final and I know y initial in this case. So let's write that equation down. Y equals y initial plus Vy initial t plus 1/2 ay times t squared. Y initial is 2.3. Y final is 0. Vy initial can be rewritten, again, in the same way we did before, as V0 times the sine of 38 degrees. That Vy0 also has a t sitting next to it, so I got to put that t there. plus 1/2 times AY, my AY is minus 9.8 in my coordinate system, times t squared. And what I can do now is substitute. I don't know this V0, and I don't want to know it. So I can do, what I really have is two equations that have two unknowns. The two unknowns are t and V0 in this equation, and the other one I've underboxed, right? And you know, way back from your algebra days, if you have two equations and two unknowns, you can always solve for one of the variables in terms of the other one, substitute, and then you'll have an equation that only involves the one variable. The one you solve for first is the one that disappears. So I'm going to solve for V0 because I don't want to know anything about it, and it's going to disappear in the process. So let me just do that here. This means that V0 is equal to 22 over t times the cosine of 38 degrees, right? I just divide by t and divide by cosine of 38 degrees, and I get V0 equals. Now I'm going to substitute that back in here. 2.3, and then I'll have an equation that only involves t, and I'll see if I can get a solution out of it. 2.3 is equal to, where am I here? V0 times the sine of 30, I'm sorry, I'm supposed to be plugging in my V0. We're plugging in for V0 that we got up there. My V0 is 22 over t times the cosine of 38 degrees. That's my V0. That was multiplying the sine of 38 degrees and also multiplying a t, right? This whole thing right here is my V0, and I just substituted it in. Let's see, minus 9.8 divided by 2 is minus 4.9 times t squared. Okay, now how can I simplify that mess that's right next to the equal sign? What cancels in the numerator and denominator there? The t, and that's really nice. I'm super happy that that t cancels out, numerator and denominator, because then I'm just left with only one t location in this equation. I can just solve for it rather than using the quadratic formula or something worse, you know. And then I'm ready to do it. You could simplify and say, well, everybody, does it sound familiar that by definition, the sine of an angle over the cosine of an angle is the tangent of an angle? That's just a definition. So we could combine those into the tangent, but we don't have to. So if I wanted to solve here, it's a little bit of a mess the way I've written it now, but I would say that t, if I solve for t squared and then take the square root, that would be 22 times the sine of 38 degrees over the cosine of 38 degrees. The t's canceled out, minus 2.3. And then I'd have to divide by 4.9. You could do it a couple steps at a time and then unsquare it to get the square root of this mess. I'm doing some mental gymnastics there, but you could do it in several steps if that's fine. Okay, that number, not an interesting number, 1.994 is what I got out of my calculator. Approximately equal to 1.994 seconds. That's how long that football's in the air. Okay, that's the hard part of this problem, but it is hard because you can see by not being given this initial speed, the only difference really between this problem, there's two differences. One is, in the previous problem, I don't think we were given this distance and we were given the initial speed. And that apparently made things a lot easier for us because I knew what the initial x and y velocity components were. Here, I kind of had to hold my breath and say, I don't know what the initial speed was. I'll just give it a name and hope I can get rid of it later on because I don't know anything about it and I don't want to. The other thing that makes this a little bit more difficult is that the final and initial heights are different. And a lot of times that might mean that you end up having to use the quadratic formula. In this case, we somehow got rid of it here. Now, I think that will help you go through the next few. So I want you to work on, try to do B, C, and D just here. Spend a few minutes doing those. They are, well, I guess, how am I going to figure out B? I claim is if you look at the work on the board, you're all but done with B. Why is that? Yeah, we've got an expression for V0 right here, and we just figured out what T was, so that's good. That's kind of like, when you're solving two equations and two unknowns by substitution, and you solve for the one after you've eliminated the other one, you can always substitute back into that previous equation to get the other variable if you've got two equations and two unknowns. That's all we're doing in B. But I think C and D are kind of like stuff we've done before, but good practice. But my memory tells me that there's some homework problem that's kind of like this. So, if you run into this, you don't know the initial speed, you might just hold your breath and go back and look at these notes. He also told me he had to leave early today, so that was planned. All right, my answer's up here. I got what looked like exactly 14 meters per second if you kept a lot of places. Oh, 3.79 meters. Okay, let's finish it up together. Again, for B, all I did was substitute in this the answer for T that we got before, and I got about 14 meters per second, so not much more to be shown there. C, what maximum height above the ground does the ball reach? Now, in my initial and final that I've chosen over here, neither of those has to do with that maximum height, so I might want to change my mind now about what the final is, or the initial, but I want one of them to be at the maximum height. So I'm going to change my mind from before and say the final is at the maximum height. Because otherwise I'm not going to find anything out about the maximum height. And then the answer I want is y final, right? That would be the answer I'm looking for here. And, well, let's see. If I want y final, I just go over to my equations and I say I have two choices, y versus t, or here y is expressed in terms of vy final. The problem with the t one is that in this case, I don't really know how long it takes to get between this initial and the final that's up there. It's not half of the total time we solve for because we're not talking about a symmetric parabola anymore. It is a symmetric parabola. We're not talking about the same points, right? This amount of time is going to be longer. This one's shorter, so I can't just divide by 2 here. So that equation seems like it's going to be problems for me to solve for y final. So let's go for this one because I do know something about vy final. Vy final squared equals Vy initial squared plus 2ay delta y. And it's that delta y in between initial and final. Well, in this case, we want to know the height above the ground, so maybe it's best to write this as y minus y initial. What we want is y final. That would be the height above the ground in my coordinate system. What's Vy final? It's 0 for my new final. Vy initial, well, I haven't calculated it, but I've almost calculated it because we've already calculated V0. So if I know V0, this means that, well, we'll do a little side calculation over here. Vy0 is going to be V0 times the sine of 38 degrees. And V0 was 14, so that's 14 sine 38. That number, 8.619 meters per second. So now I know that. 8.619 squared. You've got to be really careful. That's a y component of the initial velocity vector. We can't just throw in the initial speed there. We have to make sure we're getting just the initial y velocity component. And I didn't, for a moment, maybe I panic and then say, oh, wait a minute, I know what goes into that. We've already worked out most of the details there. Plus 2, ay is minus 9.8 in my coordinate system because I chose plus y going up. And this is y minus, what was y0? 2.3. Oh, I see. My answer is wrong in here because I solved for delta y. But delta y, the question is phrased as, what's the height, maximum height above the ground? What I solved for in my solution here, I'm going to have to correct it and rescan it before I post it today. I solved for the change in height from the throwing height up to the maximum height. That's not what's asked for. So here, I really want y final, right? In this coordinate system, y equals 0 is down at the ground, right? So we want to know this is going to represent y final, that whole distance. And so that's what I got to solve for here. So my number was delta y, but I've got to add 2.3 onto it. So I got 3.79, 2.3, so that's going to be 6.09, I think, if I did that correctly. Y equals 6.09 meters. Hopefully I did that correct in my head. Questions about that one? Again, not too bad. I'm just, every time I'm going over to those kinematics equations saying, which ones have the thing I'm looking for, eliminate the ones that look like bad luck for me, and then there's usually a best contender. Finally, D, what's the ball's speed just before hitting the ground? Well, in D, I know the speed just before, and again, I probably want to change my decision about final. Since we want to know something about hitting the ground, I'm going to say final is hit ground. You got to at least have that definitely in your head, whether or not you write it down. It definitely helps me on an exam, too. If you've written it down, then I kind of know what you're thinking. It helps me interpret what your work means and give partial credit. So this would be the square root of Vx final squared plus Vy final squared. Do I know anything about Vx final? What do I know about it? Yes, the final is equal to the initial. Again, that's from this equation. Ax is 0. It's not accelerating along x, so the final is equal to the initial. I haven't really calculated the initial, but I've all but done it over here. It's just V0 cosine 38. That number, when you crank it out, is 11.03. Plug in the V0 we found. 11.03 meters per second. So this is going to be equal to 11.03 meters per second squared plus, well, I haven't figured out Vy final, so I've got to figure out this and then plug it in. And so again, I've reduced it. The thing I want to know, if I only knew Vy final, I'd be done. So now I go into subroutine mode and say, how can I figure out Vy final? Well, I go over here and look and say, either one of these would work because I know the time between initial and final, and I also know how far it goes down. Let's just try the third one so I don't have to necessarily, well, we'll see how it works out. Vy final squared is equal to Vy initial squared. We already calculated Vy initial, 8.619. So let me write it down. Vy initial squared plus 2ay delta y. That's equal to, let's see, Vy then will be the square root of this stuff. Vy initial is 8.619. That's getting squared. Plus 2 times minus 9.8 times delta y in between initial and final. What's that number? Looking at the diagram over here. Again, we're taking the original initial and final now. What's delta y between initial and final? It's minus 2.3, right? Y final is 0, Y initial is 2.3, so Y final minus Y initial is minus 2.3, or it goes down by 2.3 meters. That makes me feel good. I don't want, I already had a minus sign here under the square root. It's nice that that's sort of canceling out. Otherwise, if this negative number were bigger than this positive number, I would be taking the square root of a negative number, and I wouldn't know what to think. Okay, so that Vy final ends up being 10.93. Lots of not interesting numbers. And then I plug that back up here to figure out what the speed is. I figured out what Vy final is. I already knew what Vx final was, and I get 15.53. The Vx final was from, the Vx final is the same as Vx initial, and we already solved for V0. Oh, I'm sorry. Vx final, Vx final was equal to Vx initial. That's from one of our kinematics equation because Ax is 0. So Vx final is Vx initial. And Vx initial was V0 times the cosine of 38, and we figured out what V0 was already. I know. it's complicated. I told you this is one of the harder varieties of these problems, but I wanted to make sure that we tried some of these in class. Other questions about this part? All right, I want you to spend about 5 minutes thinking about how you might do problem 4. In problem 4, a soccer ball is kicked from ground to the ground, which sounds, hey, that's pretty easy. It's starting at the ground. It sounds easier than this one. And we're given some perfectly reasonable information. We're told that it goes a total distance of 26 meters from the kick to the point where it hits the ground. And we're told that its maximum height above the field is 10 meters. Perfectly reasonable information. And the question is, first of all, how much time it's in the air, and then second of all, at what angle was it kicked? The difficulty is I've got to use both the 10 and the 26. Now the 26 seems to be associated with an initial here and a final over there. But if I use this initial and this final, the 10's not going to come into anything because the 10 doesn't have anything to do with this point and this point. It has to do with something halfway in between. So I'm going to have to use a mix of initials and finals and say, use the fact that whatever time it takes to get from here to here, it's exactly half that time to get from there to there or there to there. So you might, just to give you a hint, you might take this highest point as your initial, and this right before it hits the ground is your final. And that actually helps you a lot, because if I write down y as a function of t, the nice thing that happens in y as a function of t is, because I've chosen that to be my initial point, vy0 is 0. It's going totally horizontally at that particular initial point. And that means this linear term goes away, and the only t that exists in there is this t squared. So I don't have to use the quadratic formula in solving for t. So you can first solve for t that way. That will be exactly, the time it takes to get from there to there is exactly half the time that is the answer to the problem by the argument that we already gave, that you can divide that parabola in two. So see if you can answer A, and maybe because the hour's getting late, we'll do B and C together. All right, let's finish up together here. probably, if you're following what I'm saying here, you might have had enough time to do A now. I got 2.857 seconds. The idea is I've chosen my initial to be here and my final to be there, so I can use this 10 meters. That's something that's going to involve that 10 meters. And I want to know the time this ball is in the air between kick to hitting the ground. If I can find the time between what I've labeled as initial and final, the time we're looking for is just double that time. So I got to keep that in my head. Let's find a certain t, and we're going to double it at the very end. And now I'm going to use y versus t, and we'll see again why choosing the initial at the very highest point is really advantageous. Y final, oh, I didn't draw any axes on here, but let's do the usual ones. I'm going to put the kick point to be the origin and x along the direction of the kick and y upward. Okay. Y initial in my coordinate system would, sorry, that's y final. Y initial is, no, y initial is 10. Y initial is here. So the initial y coordinate is 10 in my coordinate system. Yes. It's getting too late for me, obviously. Okay. Y initial is 10. Y final is 0. Thank you very much. Vy initial, this is why it's so nice to use that point as initial, because Vy initial is 0. It's only moving along the x direction at that instant in time. Plus 1/2 minus 9.8 times t squared. And then we take this, solve for t squared and take the square root, and I get t is equal to 1.429. And it's very tempting to then box that number, but then I got to remember, wait a minute, that's not the answer to the question. The answer is double the time we just found out. So my answer is going to be 2 times that. 2 times t is equal to 2.857 seconds, which answers part A. Any questions on that? So part of what's a little bit, it seems like, oh man, it's just so simple. All these nice things are given there, but the two pieces of information that are given are sort of not consistent with the same initial and final being used. So in this case, I chose one of them to help me figure out t. I still haven't used the 26 meters, and that's going to come into the next one. At what angle above the horizontal is the ball initially kicked? Okay, so in this case, because the final, at least I already know a lot about what's going on up here at the highest point. In part B, I chose my initial to be the kick and my final to be the highest point. Just to be clear about that. Okay. And we would like to know at what angle above the horizontal it is kicked. In this case, if I chosen my initial to be here and the initial to be here and final there. I better change this or I'm going to get messed up because I'm getting tired. Initial, final. What that angle theta is going to come into my Vx initial and my Vy initial, right? So in this case, I could say in terms of the, if I imagine holding my breath and saying, I don't know what speed it was kicked with, but let's say the speed is V0, then just like we've done before, Vx0 is going to be V0 times the cosine of that unknown theta, and theta is what we're asked for here in B. Similarly, Vy0 is V0 times the sine of theta. And I'm just going to plug those in and hope that somehow I can get my theta out of here. Okay? So, writing down, because Vy is particularly simple at the final point, let's write down Vy as a function of t. Vy is equal to Vy0 plus Ay times t. Vy final is 0 for my final there. Vy initial involves the thing that I want. That's V0 times the sine of theta, plus Ay is minus 9.8. And the t, what t do I want to use here? In between initial and final for what I've got it defined as there, is it 2? Yeah, it's the 1.429. That was the amount of time between here and here, which is the same as between there and there, because everything's symmetric for a parabola if we plot y as a function of t. So I already know that number, 1.429. You really got to keep your head sort of straight with this stuff. Unfortunately, I still have two unknowns in there, V0 and theta. So I'm just going to kind of, did I solve for anything? Yeah, here I said I multiplied these together, and I can therefore figure out that V0 times the sine of theta is equal to a number that's very close to, or maybe exactly equal to 14 when I multiply those together and put them on the other side of the equation. I'm putting an underbox on it because I've got two unknowns still. I need another equation here. And the other equation I can use is, again, for the same initial and final, I know not only how far it goes up in y, but how far it goes in x. How far does it go in x? Not 26 meters for my initial and final, but 13, half of it, right? So let's substitute in, again, for that, I'm going to here use x as a function of t because I know the t to plug in. X final is equal to x initial plus vx initial times t plus 1/2 ax t squared. Let's not forget that ax is 0, so that makes me happy. X final, for this is initial and this is final, is 13. X initial is 0. Vx initial involves the same two unknowns that I had before. It's V0 times the cosine of theta. And the t I'm going to use is the same amount of time. I'm using the same initial and final. So that t that I plug in right there is 1.429. And the last term is 0. Okay, that allows me to solve for V0 cosine of theta. And what is that number? 9.097. Okay, let me put an underbox under those. And now, yes, Sam.
Could you not find the Vx by doing the distance divided by the time?
You mean find Vx0? Yes, I could find Vx0 that way. And yes, that essentially is what we did right here, right? We had the distance times the time. So I could have figured out, let's see, the distance it went, and we know the time, the amount of time that it took. Yes, so I could have calculated that number, which would represent this number, and that would still be equal to V0 cosine theta. So I think that's just a different way of getting at it here. So I think you're right, Sam. But I would end up still, I don't want to know Vx0, I want to know theta, right? So I need another relationship between V0 and theta. And so here it is. Sam suggesting a different way to get at that number, maybe a little bit conceptually simpler. Now, the question is, given these two equations, how do I solve for theta? And this is a little bit subtle if you're not used to working with trig functions. I could just solve and substitute, right? I could solve, I don't want to know V0, so I could solve for, you know, maybe solve for V0 here. V0 is 9.097 over the cosine of theta. V0 is 9.097 over the cosine of theta. And then, unfortunately, my theta is in two locations, but it's not really, if you remember that trig identity, sine over cosine is tangent. This is telling me that 9.097 times the tangent of theta is equal to 14. That's a little bit subtle. I promise you I wouldn't put something like this on your exam that we're going to do. But, you know, this stuff does come up sometimes. I don't even think there's one like this in the homework. There certainly is one like the previous problem. But then I can divide by this and then take the inverse tangent of both sides and figure out what theta is. When I did that, I got 57.0 degrees. Okay. And that answers B. And C, I claim, is really easy. What's the ball's speed at the maximum height? How could I figure that out from what we've got on the board there? Say that again. Yeah, it's Vx0. Vx is equal to Vx0. Its speed doesn't change as time goes on. So let's see. Well, we certainly could figure it out by Sam's method, but we now know the theta. I could, if I wanted to sort of go with this logic here, I could then say, now that I know what theta is, I could substitute in here and get V0, and then V0 times cosine of theta is Vx0, and that's the same speed that it has at the highest point, because Vy at that point is 0. That's for sure the hardest problem we're going to encounter. I think it's harder than the ones that are in the homework. That I would consider, you know, the third one probably as hard as they get in the homework, and there's maybe one or two that are at that level. Most of them are easier than that. But I didn't want to trick you and do all easy problems in here. We'd feel good till you went to do the homework, hopefully not Friday night at 11 o'clock. So take a look at that homework. You'll see a lot more practice with this kind of stuff in there.